All right, everyone. Please welcome Dr. Marcelo Gleiser. He is an Appleton Professor of Natural Philosophy and a Professor of Physics and Astronomy at Dartmouth College. In 1994, he received the Presidential Faculty Fellows Award from the White House, and he's also a 2019 Templeton Prize laureate. Without further ado, please welcome Dr. Marcelo Gleiser as he dives into the mysteries of the universe, what we know and what we don't know.
Hey, hi everyone. Wow, you guys don't even take a break between talks. You're very brave. I'm very impressed. That's pretty cool. And it was a very nice lecture by Professor Henry about his work and what he's done. I could address some of your questions. When we come to our questions, you can ask them again, and I'll be happy to do my best to answer them. So that would be great. But let's go on because we don't have a lot of time, and so let's make sure that we talk a lot about what I do and how it's that interesting to you as a potential future career, right? So let me put on my share screen here because I want to show you my transparencies that I prepared for you because everybody loves a pretty picture. Um, and can you see that? Just Diana, give me a thumbs up in case you guys are sharing. You can see my shared screen. Yes.
Yeah, yeah.
All right. Cool. All right. So what I'll do in these 20 or so minutes is essentially tell you a little bit about the history of the universe. There may be some overlap with Professor Henry's talk. I didn't watch the whole thing, but hey, it's always nice to learn more stuff, right? And it's very descriptive, and there's no math at this point, anyways. And so let me introduce myself. So Marcelo Gleiser is my name. I am a theoretical physicist. I work mostly on what is called the interface between particle physics, so the study of the very, very small, and cosmology, which is the study of the very, very large. And you may say, how is that even possible? How could someone be studying both the very small and the very large at the same time? And the reason for that is that if your main area of interest is this area of physics that we call cosmology, which is the study of the universe as a whole, then you learn very early on that the universe has a history, right? It has a big bang, sort of like the origin of everything. And at that moment that we don't quite understand at all, but at that moment in time, matter, energy, everything was very concentrated, very high densities, very high pressures, very high temperatures. We don't really have the physical tools to describe that. But once the universe starts expanding and cooling off, and time starts to roll forward, so to speak, then we do have a lot of understanding of the physical processes that took place early on in the universe. And very, very early on, the universe was so hot that there were certainly no people, no stars, no molecules, not even atoms, not even protons and neutrons. Everything was broken down in the smallest possible constituents, which are the particles that make up all of matter. So essentially, the early history of the universe is a history that is told by the wedding of particle physics and general theory of relativity, which Professor Henry mentioned that. I think that's when I joined in. He was talking about Schwarzschild and his solution of the black hole, right? Essentially, the idea that there is a singularity in space if you have a concentration of mass that goes beyond a certain value, which is the Schwarzschild radius. But the point is that so essentially this theory of general relativity that describes the history of the universe as a whole that Einstein proposed in 1915 has been married to the physics of the very small. So we call it kind of romantically, we call it the inner space, outer space connection, right? And that's pretty much where I've done a lot of my research, which also bifurcates into another area, which is the origin of life on Earth and the possibility of life elsewhere, which is generally called astrobiology. So I will try very briefly to talk a little bit about all these things as we move on. So let me start by playing the slides for you guys. So we have here these two pictures, right, which I think are very cool because on the one where you see the stars and the sky, it's a vision that we all have if you're lucky enough to live far away from the big city where you do have bright skies, and if you have a pair of binoculars, you'll be able to see not just the new ice comet, well, not anymore, but whenever it was showing up, but you'll also be able to see a bunch of stars that you cannot see with the naked eye, right? So the stars that appear to the naked eye are definitely not all the stars that exist. And a lot of science, and this is something which is really, really very important, is in a sense a way that we found through time, we meaning humanity, found through time to amplify our connection to nature. And we do that by amplifying what our senses can perceive of reality, right? Because if you think about it, you can only see a very small spectrum or very small window of the so-called electromagnetic spectrum, right, which is between the red and the violet. Everything else, the microwaves, the infrared, the ultraviolet, and all the other frequencies of light are invisible to the eye, which doesn't mean they don't exist. It just means that you need the right tools in order to open up those windows to this invisible reality that is all around us. And that's exactly what science does. It sort of amplifies our perception of the world and of the universe, right? And so on the side here, you have the stars, and everyone has gone out one day in life or more, if you become a scientist, and wondered what is going on. Why are there so many stars? What are stars? How do they come to be? What is the relationship between those stars and ourselves and our own star, the sun? And can we use science to make sense of all these questions? And then, of course, you start asking, why are we even here? What is the meaning of our being in this planet at this moment in the history of the universe? So these are sort of like questions that sound philosophical, even metaphysical, but that are now very much part of what science deals with, the big questions of existence from a scientific perspective. And the other image that I have here, I don't know if you can see that with your screens, but basically you have here a tiny little point of light, right? And this beam that is kind of highlighting it. Well, that tiny little point of light is planet Earth seen from Saturn. This picture was taken by Voyager 1, a NASA probe that was sent in the 70s to kind of fly by the outer planets. And Carl Sagan, the great Carl Sagan, had this great idea of let's turn the camera of Voyager 1 when it's going by Saturn to take a picture of the Earth seen from Saturn. And this is what you see. So this is where we are, right? If you lived in Saturn and you could take a picture of it with a good telescope, that's why you would see this tiny little blue dots. Doesn't look blue here, but that's what it really is. And that is our planet in this vastness of space. And so you got to wonder, and people have wondered about our origins and about where it all came from the beginning of time, right? As soon as our ancestors were running around the African savannas, they were looking at the skies, they were thinking about the meaning of life and trying to make sense of everything. And really, if you think about it, the whole history of science, right, is asking questions that these people were asking before, which is, where did we come from? And indeed, if you look at a bunch of different religions, right, spread across history and across the whole planet, pretty much all of them have some sort of narrative of creation, right? I mean, where did the universe come from? Where did the world come from? Where did life come from? And these are the questions that motivate cosmologists and that motivate the people that study astrobiology, or the origin of life on Earth and elsewhere in the planet. So, in a sense, we are heirs to the same questions that have been asked for thousands and thousands of years, but we now have this advantage of having the tools and the mathematics to actually probe them in a very, very deep way, right? And this is why, since I was kind of young, like even before like being in college for sure, And I was fascinated by the power of science and human reason to ask these questions and to provide answers, not always complete answers. We still have all sorts of mysteries out there. And Professor Henry mentioned one, which is very important, which is the mystery of dark matter, right? The fact that 26% of the stuff that fills up the universe is unknown to us. We know how much is there because this dark matter has mass, and because it has mass, it can bend space according to the general theory of relativity. So we know it's there, but we don't know what it is. And then only 5% of the stuff that fills up the universe is made of the normal things that we consider matter, like the electrons, the quarks that make up the protons and the neutrons, and the photons that make up very little of this whole stuff, and neutrinos. So all of that makes less than 5% of all there is. There's this 26% of what is it? But then if you do the math, say, wait a second, 26% plus 5%, it's 31%. What happened to the other 69%? Well, that is called dark energy, which is an even bigger mystery than dark matter. And that one is essentially what's making the universe not just expand, but accelerate in its expansion, right? So that is kind of like, what the heck is this? What could be possibly making the fabric of space itself stretch out like if it were a rubber sheet, and that is the mystery of dark energy. So if you make the calculations and say, wow, so despite everything that we have learned about the universe, we really still don't know 95% of the composition of what's out there. Now, if that's not enough mystery to motivate someone young to go into physics, to go into cosmology and astronomy, I don't know what it is. I mean, this century is definitely the century where at least the mystery of dark matter, I am very optimistic. I don't know if they are decaying, if the radiation is or not decaying dark matter particles, but I think that we have now the observational tools to really make progress on that question. So my guess is that in 10, 20 years, we should be understanding the nature of dark matter very well. Dark energy is a very big question still. There are all sorts of different ideas about what it could be, even ideas about maybe our theory of gravity that we use to describe the very large scales in the universe, the general theory of relativity, may need to have some fixing. But we've learned these things, and I always put these two pictures, like the big and the small. Oops, let me go back. This one here is the Horsehead Nebula, right? It's a place where there are all these stars being made, stars being formed by the power of gravity to contract big clouds of hydrogen and all the other atoms that are around there. And then when the temperatures at the core of these stars reach about 150 million degrees, they begin to ignite and start forming uh, radiation. They go from hydrogen to helium. It's called nuclear fusion process. And then the star is born, so to speak, right? And this has happened to us, meaning us, our solar system, about 4.5, a little more billion years ago. A big hydrogen nebula was contracted because of instabilities that happen due to other stars exploding in our neighborhood. So the universe is a very dynamic place. Stuff is happening all the time. Stars are being born, stars are exploding because they're dying. And this amount of stuff that is thrown out into space is actually where all the matter that is made into your bodies, your carbon, the calcium in your bones, the iron in your blood, all this stuff came from dying stars that exploded billions of years ago. So if you think that you're young because I'm only 15, I'm 20, I'm 30, I'm 80, you're not young. This agglomeration of matter is young, but you're actually billions of years old. I mean, the stuff that you're made of is really old. It's just this new conformation of matter that you call yourself that is young. And so about 5 billion years ago, the solar system was born, the sun and all the planets. And each one of these worlds is completely different from the other. So I have a picture here of Enceladus, which is a spectacular moon of Saturn, which is truly mysterious. It has all this ocean that is frozen on top, but some cracks in it. You have these geysers that erupt with some ice being spit out into the atmosphere. And there's a lot of stuff going on. There is oceans underground, underneath all of this, and they are sort of models, perhaps, not necessary for life as we know it, but for biochemical processes that could help us understand our own history in this planet. So we have learned a lot of stuff, and this is a picture that I love, is a map from NASA of the whole history of the universe together, right? So we start here with the Big Bang, right? Time is going from left to right. We don't really know what is going on here, right? My research very much is about this physics that is the gray zone here, where we don't quite know exactly what was going on, the big expansion of the universe. And the point is that as the universe expands and it cools, eventually stuff starts to happen, matter starts to agglomerate, and you have atoms forming, first hydrogen atoms when the universe was about 380,000 years old. And then you start forming the first stars when it was about 200 million years old, and then the galaxies, and at billions of years, 1 billion years or so, you start really forming the older galaxies are beginning to cluster together. And you have a whole history of how galaxies go together and cluster with one another because of gravity. So it's kind of like there is a hierarchy of clustering. So the moon is attracted to the earth because of gravity, and then the earth and the planets are attracted to the sun because of gravity, and then the sun is in a galaxy because of gravity. So there's a beautiful picture of a galaxy here, a spiral just like ours. And then galaxies are attracted to one another because of gravity, and they form these giant structures which are millions of light years across, hundreds of millions of light years across. And you come up with these beautiful pictures. For example, this one is called the Hubble Deep Field, one of the Hubble Deep Field pictures. Each one of these blurs is clearly a galaxy, but what's really spectacular about this is that each one of these fainted little things is also a galaxy, just deeper away. And so you start to think, wow, each galaxy here, right? Hold on. Each galaxy here has hundreds of billions of stars, just like our Milky Way does. And each one of the stars we now know has planets, pretty much all of them do. So you start to calculate and say, wow, there are trillions and trillions and trillions of planets and moons. Just Jupiter has more than 65 moons. And all of these, in principle, could be harboring life. So you're talking about the big scale of things, but then you start to think about, well, is there a place for life elsewhere in the universe? And how would you know, right? So we start to think about it. And then we start to realize that as we look out into these spectacular worlds out there, there's even a sub a subdiscipline in astronomy nowadays called comparative planetology, which basically is I'm looking at all these different new planets that we're discovering around other stars and studying them in comparison to each other, their mass, the distance from their star, the temperature, the chemical composition, etc., and comparing that to the Earth. And the more we learn, we realize that the Earth is a very, very special place. Not just because it has water or carbon, all of that stuff, but because it has properties that allowed not just for life to emerge about 3.5 billion years, but for life to exist for a very, very long time, almost uninterrupted. There were some very big cosmic cataclysms. One of them, I'm sure you guys know, the one that killed the dinosaurs and about 50% of life on Earth, which was 65 million years ago, but there were some much worse ones before that that almost sterilized Earth completely. But life persevered, right? And this is a spectacular picture of a solar eclipse taken by the International Space Station. So here in the bottom, you have the Earth, and you start to wonder, wow, our species, can do a lot of damage to the world, but is also a species that reversed, in a sense, the history of how planets behave. Because if you look at how a planet behaves, it's a very passive thing. Stuff falls onto the planet, right? You have radiation falling onto the planet, you have asteroid, meteorites, and sometimes comet collisions, etc. But now, because of what we have done with science, because of what our technology is able to get, all these primal materials that exist on Earth and convert them into technologies, we're able to actually start to spit out matter into the universe. So it's sort of like the anti-accretion phase in which our own technology, our own creativity now has a planet in this giant Milky Way that we know is able to have an intelligence that is capable of spitting stuff out into the space so that we can understand better our origins. So it's a beautiful story of creativity, discovery, invention, always trying to answer the fundamental questions of existence, right? And one of the things that we realize, and this is a very, very important message, and it's a message that is extremely important for your generation, is that certainly life can exist elsewhere. There's no reason why it couldn't, because the laws of physics and chemistry are the same across space. So yes, there could be other planets that have life, but we can tell you that life as we know it, super complex, multicellular, and especially with organisms that are capable of designing technologies, is going to be very rare, right? If it weren't that rare, we would probably have known about it, despite the enormous interstellar distances that make space travel hard, right? Our civilization is very young. There could be civilizations that are millions and millions of years old. We don't know about them. So, for all practical purposes, even if they do exist out there, we know that, first of all, we are kind of alone in our bubble here, in our bubble of space, in our distances. And because of that, and because we understand the preciousness of life, we have the moral duty to protect our planet, to protect other life forms. For example, one of the questions that I saw before was about, are we going to be able to go to Mars and essentially transform Mars in a place for us to inhabit? This is a possibility which is hundreds and hundreds and hundreds of years away from us. We have much more serious problems to deal with in the next few decades about how we relate to our planet and the resources and the other living creatures in the planet. So we have to be alert to the fact that we should be focusing a lot of our attention right now in our own planet and the beauty of the life that exists here, as opposed to focusing too much energy on, yes, let's go out there and not pay attention to the problems that we have here. And this is a mission for you guys. This is a mission for you guys to use science, to use technology, to do what's the most beautiful thing about science, which is not just to answer our big questions about existence, which is also to alleviate human suffering, right? And we're all in this together. And I hope that in this brief presentation, I gave you a few pointers of what you could be thinking about in terms of a career in the future. And of course, I'm very happy to answer questions.
Thank you so much, Dr. Gleiser. Let's see if there's. Oh, I know there was one more question from before that we didn't get to. Let me see. Oh, someone asked, this was from Dr. Henry's talk, but someone asked if you could, how do you integrate / use the Pythagorean theorem in physics, and where do you put the negative number?
So here's one application of the Pythagorean theorem in physics, which is a beautiful one, which is in the special theory of relativity. Believe it or not, to understand the special theory of relativity of Einstein, you don't really need a lot of math. You only need the Pythagorean theorem and some basic understanding of things moving about with certain speeds. And if you do that, you can actually show, using the Pythagorean theorem, for example, time dilation, the fact that if I have a moving clock, it's going to tick a little slower. And if I had more time, I could show you, because I teach a course here at Dartmouth that people call Physics for Poets, where I describe to them time dilation using the Pythagorean theorem in something which we call a light clock, which is basically a big room that has a mirrors on the bottom and the top, so the light can go tick tock. And if this thing starts to move, the light is actually going to go on a trajectory which is not just up and down, but it's going to go like this, as you see the light blob going up to the top mirror. And so you form a triangle. And to calculate the length that is traveled by the light that is in this moving clock, all you have to do is use the Pythagorean theorem. And lo and behold, you get time dilation, showing that a moving clock actually ticks slower, from the point of view of the observer that is seeing it moving. So that's an obvious application. And honestly, there are quite a few others. I mean, the Pythagorean theorem is quite essential indeed in physics, okay? But there are many, many other kinds of mathematics that you use in physics. I see a question here from Harry. Can you show us some mathematics? Basically, at least in theoretical physics, physics is the art of solving partial differential equations, with varying boundary conditions and initial conditions. Like every problem that you can think of in physics, from the equations of quantum mechanics that describe how electrons jump around different levels of an atom, to a spring oscillating, a mass oscillating on a spring, to equations that describe the curvature of space around a star. All of these equations are equations that use what we call partial differential equations. So basically you have a function that has more than one variable. You have to take derivatives with respect to all these variables, including time. And by solving those equations, you figure out, depending on your initial conditions and the boundary conditions that you have, what will happen to your system. Okay, so if you want to know what is the equation that calculates the propagation of temperature in a room, so you heat up a room on one side and you want to know what the gas is going to do or a surface is going to do as it heats up, that's the diffusion equation, and you calculate that using partial difference. So they're all over the place. And that is why I guess Galileo, when he started to kind of invent this whole thing, he said that mathematics is the language of nature. He was actually inspired by Plato, who came much earlier than him. And Plato was inspired by the Pythagoreans that came much earlier than him, 650 BCE. But the notion is that we humans have this incredible ability to find mathematical patterns in nature, and we use that to describe to the best of our ability what's going on.
Oh, someone also asked, is it possible that planets such as the Kepler 452b could develop intelligent life in the future similar to Earth's history?
Well, I can tell you this: no two planets in the universe, and that's quite a statement, no two planets in the universe will have exactly the same kind of life. And the reason for that is that the history of life in a planet, how it evolved from very simple unicellular organisms on, or just stays a unicellular organism, depends very much on the planet's history. In the sense that if you look at what happened to life here in the last 3.5 billion years, the evolution of life is very much contingent and codependent on the history of all the collision impacts that happen on Earth, all the big cataclysmic events, the giant eruptions of magma that existed during the cooling of the planet and because of tectonic plates moving about. So and this is a beautiful thing, every planet that has life will have a different history because the planet has a different history. So we should not think that there'll be something similar to us. In fact, we should say, kind of proudly, really, we are the only humans in the universe. Because even if you have other forms, even similar, with this left-right symmetry that we have, bipeds, etc., they will certainly not be just like us because the history of their planet is not going to be just like us, which opens up this incredible space of possibilities for the histories of life in other places. So intelligence is not a necessary outcome of life. This is something very important, and people tend to confuse that. One of the greatest biologists of all time, Ernest Mayr, he always said that life is about adapting to an environment. If the environment changes, those who have better adaptations will persevere, and this is what natural selection is, right? But there is no arrow of complexity in life that tells it that it needs to go from very simple to intelligent. That's not what life is about. Those were contingencies that happened to us here. So, for example, if the so-called asteroid that hit Yucatan Peninsula 65 million years ago, which I told you about before, had not hit, dinosaurs could still be around. And there's no reason to believe that they will be very smart because, they were around for 150 million years before this, and they had not, as far as we know, developed language, radio telescopes, poetry, symphonies, or anything like that, right? So if life is well adapted to an environment that doesn't change, it doesn't necessarily change or become more complex. So if you look at the many, many steps for life in a planet, you realize that it is really hard to predict. And in fact, I forgot to put this, which are some of the books that I have written for general audiences, but they're pretty heady books, And this particular one here, A Tear at the Edge of Creation, talks a lot about life in the history of life on Earth, the importance of asymmetry in physics and in biology. So this would be a good one if you guys want to learn a little more about this stuff.
Yeah, definitely. Anyone else? Any last thoughts? Questions?
I'm pretty sure there's some questions that there's one beneath the one he just answered.
We also use a version of Pythagorean
No,
theorem. That's a comment. Yeah.
Oh.
Yeah, that's a comment.
Mm-hmm.
Okay. Well, I wish we could
good.
talk more. Yeah, both of your talks were very fun to listen to, but we are on a rather tight schedule because we have so many events today. Awesome.
Yeah.
Dr. Holtz just commented the link of the book if you're interested.
Oh, cool. All right. Thank you. Well,
I'll
thanks
put it
everyone.
in the YouTube chat too.
And if you have any big
Thank you so
pressing,
much, Dr. Gleiser.
My pleasure. If you have any big pressing questions, find out my email. It's very easy if you know my name, and fire them on. And I'll try to answer them to the best that I can. Okay? All right. Talk to you soon, guys. Bye.